Good morning, student. Today we are going to see determination of ion exchange capacity. In actual practice, about 0.5 gram of dried resin in hydrogen form is accurately weighed and transferred to the column partly filled with distilled water. Some more distilled water is added so that the resin completely cover. Care is taken to remove any air bubble on the resin. With the help of separating funnel, about 200 ml of 0.25 molar sodium sulfate solution is dripped into the column at the flow rate about 2 ml per minute. During this process, hydrogen ions of the resin get exchanged with the sodium ions of the solution and gets eluted. So basically, your resin which are in the hydrogen form and your solution contain sodium ion. So in this reaction we see that sodium ions basically replaces H plus on the resin and H plus comes into the solution. Elutant is titrated with 0.1 molar of sodium hydroxide solution using phenolphthalein as an indicator. From the concentration of hydrogen ion and weight of the resin taken, one can easily calculate ion exchange capacity from following formula. Ion exchange capacity is equal to N multiplied by V divided by W, where N is normality of NaOH, V is volume of NaOH, W is equal to weight of the resin. For anion exchange resin in chloride form, 0.5 molar sodium nitrate is used to exchange chloride ions with a nitrate ion. So basically, for anion exchange, a resin which have chlorine atom associated with it is taken and your solution of nitrate. When this solution of nitrate comes in contact with the resin which have chlorine atom on it, so your chlorine atom basically goes in the solution and nitrate replaces your chlorine atom on the resin. It is titrated with 0.1 molar of silver nitrate. So basically this solution of chlorine is then titrated with silver nitrate solution using potassium chromate as an indicator. Now we are going to see factors affecting ion exchange equilibrium. This question is important. It is generally asked in the examination. So first factor is nature of exchanging ion. This factor is subdivided into 2 points. First is charge on the ion. At a low concentration of a solution, the extent exchange increases with increase in a charge on the ion. That is, the extent of exchange follows the order sodium plus is less than calcium 2 plus, which is again less than aluminium 3 plus, which is again less than thorium 4 plus. So in this case we see that ion having less charge have less ion exchange power. As the charge on the ion increases, the exchange capacity of that ion is also increases. Size of second sub point is size of hydrated ion. When charge on the ions is the same, the extent of exchange decreases with the increase in the size of hydrated ion. For singly charged cations, the extent of exchange follows the order lithium plus is less than H plus, which is again less than sodium plus, which is less than ammonium plus, which is less than potassium plus, which is less than Rb plus, which is less than Cs plus. So in this case, just note that lithium plus have, it should be noted that the size of hydrated ion of lithium is largest. So lithium plus hydrated ion is the largest in size. That's why it's have least ion extent of exchange. So it's is largest, and so exchangeability is a minimum. When charge on the ion in the solution is higher than in the resin, dilution of solution increases the extent of exchange. When charge on the ion in the solution is lower than in the resin, concentration of a solution increases the extent of exchange. Second factor is nature of the resin. Adsorption of ions depends upon the nature of functional group in the resin. It is also depend upon the degree of cross-linking. First is which type of functional group is present in your resin. Second is degree of cross-linking. As the degree of cross-linking in the resin increases, the resin become more selective towards the ion, whose effective size is smaller. A good resin should possess a following property. It must be sufficiently cross-linked and should have negligible solubility. It should be sufficiently hydrophilic to permit diffusion of ions at finite rate. It should contain sufficient number of exchangeable groups. Solid resin should have higher density than water. This is the table with some resin name and their framework material and which type of functional group is present in that resin. So trade name, first column is of trade name, second is type of resin, third one is of framework material, fourth one is which type of functional group is present in your resin. So trade name of resin is Amber Light 400. This resin is strong base anion exchanger resin. Framework material, that is polymer which are used, is styrene divinyl benzene copolymer. Functional group present in Amber Light 400 is CH2N plus CH3 by 2. Second resin is Diolite 303. It is weak base anion exchanger resin. Framework material, it is phenol formaldehyde, and functional group is phenolic OH. Third is Amber Light 120. It is strong acid cation exchanger resin. Framework material is styrene divinyl benzene copolymer, and functional group is SO3H, that is sulfonic acid group. Next resin is Amber Light 50. It is weak acid cation exchanger resin. Framework material used in Amber Light 50 is metha-acrylic acid divinyl benzene, and functional group which are present is carboxylic COH. Next resin is Dovex 50. It is strong acid cation exchanger resin. Framework material which is used in this resin is polystyrene, and it contains functional group sulfonic acid SO3H. Now we are going to see application of ion exchange. Now ion exchange technique is used in separation of zinc and magnesium. For separation of zinc and magnesium, they are converted into their chloro complex, that is ZnCl4 2- and MgCl4 2-. The mixture of these complexes is poured from the top of an anion exchanger column. Magnesium is eluted using 2 molar HCl. Zinc remains in the column when HCl is added. After complete collection of magnesium, zinc is eluted using 0.2 molar HNO3 solution. Further analysis of the separated solution is possible using complexometric titration with the help of EDTA. Ion exchange technique is used for the separation of cadmium and zinc also. Cadmium and zinc form strong chloro complexes with HCl. They are negatively charged and can be separated by using anion exchanger. The mixture is added to the anion exchange column. Zinc is eluted first with 2 molar NaOH solution. After complete elution of zinc, cadmium is eluted with 1 molar nitric acid solution in the form of cadmium nitrate. The zinc and cadmium in their respective effluents may be determined by the titration with the standard EDTA. Next application is in separation of chloride and bromide. Anion exchange column is converted into nitrate form by passing concentrated NaNO3 solution. Concentrated solution of mixture of chloride and bromide is then added from the top of the column. These ions are eluted by adding NaNO3 solution from the top. Chloride ions are eluted first, then bromide ions comes out. The fractions are titrated with standard silver nitrate solution using adsorption indicator. Thus, it is possible to calculate concentration of Cl and bromine ions in the mixture. Next application is in separation of lanthanide. This application is very much important. Lanthanide series elements occur in the nature in various ores. These ores contain at most all the lanthanides together. Separation of this lanthanide is a difficult task. As they resemble in most of their properties, they have almost similar size. All of them exist in +3 oxidation state, so they have equal charge density. So it means that separation of lanthanide is very hard, or it is very difficult task, because they have all of them have similar size, same oxidation state, that is 3+, and equal charge density also. Ion exchange technique is the most rapid and effective general method for the separation and purification of lanthanide. The mixture of lanthanide is poured into cation exchanger column of Dovex 50 in hydrogen form. They get exchanged with hydrogen ion as follow. Now just see here your lanthanides which are present in 3+ state, when it is come with the Dovex 50 in hydrogen form. So basically your hydrogen get replaces with your lanthanides. They are eluted using ammonium citrate and citric acid buffer solution. The smaller lanthanide ions like La3+, Ce3+, etc. form strong complex with citrate ion and eluted out first, while larger lanthanide ions like Lu3+ are eluted later. So just see here this resin which is attached with lanthanide, it is reacted with citrate buffer and it going to be a form of complex. Next important application is in deionization of water. Deionization of water is carried out by natural water, by passing natural water through two columns. First column is of acidic cation exchanger in hydrogen form. This column replaces all the cations with H+ ion. Second column is of basic anion exchanger in a hydroxide form. It is important. First column is of your hydrogen, it is cation exchanger in hydrogen form. Second column is of basic anion exchanger in hydroxide form. This column replaces all anions with OH-. These H+ and OH- ions combine to give pure water. Next application is in a separation of sodium and potassium ion. Separation of sodium and potassium ion can be achieved by passing their solution through cation exchanger in acidic form. Elution is carried out by using 0.7 molar hydrochloric acid solution. Sodium being less firmly held, move down the column more rapidly, while potassium elutes out afterwards. From this solution, solvent is evaporated and chloride salt are redissolved in water. Mohs titration with AgNO3 is used for the analysis. Separation of Ni2+ and CO2+ can also be done with the help of your ion exchange technique. This separation can be achieved using strong base anion exchanger resin solution of the ion. This separation can be achieved using strong base anion exchanger resin. Solution of this ion is prepared in 9 molar HCl solution in which cobalt 2 plus form chloro complex, that is COCl4 2 minus, but nickel does not react. This complex is retained by the resin while Ni2 plus passes unaffected. After complete elution of Ni2 plus, CO2 plus is eluted by using 3 molar HCl. The separated solution can be analyzed colorimetrically. Nickel 2 plus or nickel is estimated using DMG, while cobalt is estimated using 1-nitroso 2-naphthol. In next class, we are going to see solvent extraction technique. Thank you very much.